RSA encryption decryption algorithm. It's a very straightforward algorithm, and it's called RSA, the initials of three guys that came up with this in the 70s, and it's a very popular encryption algorithm. Now look what happens. According to the, so you have two people. So for instance, Alice, whatever, wants to send a message to Bob. So let's assume Alice is going to send a message to Bob. Bob is the receiver. How does it get there? Now you're going to pick two prime numbers, 11 and 3. Those are the two prime numbers. Then you say calculate n. To calculate n is p times q, 11 times 3, which is 33. Then calculate the value for 5, which is p minus 1 times q minus 1. That's going to be 10 times 2, which is 20. Now, here's a major part of this algorithm. You're going to pick e and d, but the condition is that if you take e times d, you take the mod with 5, and phi in this case is 20. The remainder should be 1. 21, which is e times d, modulus 5, which is 20, that should equal 1. I used the extended Euclidean algorithm, and I wrote this partial code there, and this is the part that does the GCD. So it's called GCD, so you pick n and d and you go back, check, and return d. Otherwise, keep doing it. So that gives me the proper values for a and d. If I'm not able to follow this, like e times d modulus phi, if that's not equal to 20, I have to repeat until I get the answer. Because that gives me the public key value. Public key is n and e. Well, n is 33 and e is 3. Now, here's the message that Alice wants to send to Bob. So the way to do it, we have to encrypt it, which is known as the ciphertext. So we take 14, raise it to the third power, which is 2744. You mod it by 33, and 33 is the value of n. That gives me 5. 5 is the ciphertext. 5 is what gets transmitted to Bob. Bob receives this message, which is encrypted, and it is 5. So it needs to be decrypted. So we get a public key here, and I wrote the steps on the left side of this board. So you get the public key, and the public key is going to be n and d, 33 and 7. Notice the private key. The private key is n and e. The public key is n and d. So they are basically, telling me which is private, which is public. I would have to do a decryption. So to decrypt it, I take 5 to the 7, 78125. I mod it by 33, which is n, and that should give me 14. As you can see, 14 is the message that was originally sent. So the remainder here, r is equal to 14, which is exactly the message that was transmitted. If you look at my partial code here, p is 3, q is 7, I get n times p, p times q, I get 5, which is p minus 1, q minus 1, and then this is my condition. See, I'm going to say as long as e, okay, is less than 5. I'm going to call GCD. I pass E and I pass phi. See, those are the two values. If I pass E and phi, if the result happens to be 1, I'm going to quit. I exit. Otherwise, increment I, test the loop again. Call the GCD function, pass E and phi. Check if it's equal to 1. Eventually, it will equal, it will break. So now I have the values for E and D. And I could go back here and basically apply these two steps here, how to do the encryption and how to do the decryption. I left that out in the code, but that's a matter of just a simple substitution. So Bob gets the message. and it gets decrypted back to 14 to the original message. Now here's the other issue. The bigger the number is, it becomes much more challenging to get a result. You're going to have a very huge number, and if you're using Python, that's not going to be an issue, but if you're using Java, you may end up using big integer because some of these values are huge. You know, I can, if E was like 11, 14 to the 11 gives me a large number. So I can pick up, you know, and Python doesn't have an issue with this, but with Java you're going to have to use big integer to do the calculations. The point is, once I get a result and I get to the final result I want, to do the decryption, you know, go back to the original, that can be a challenging example. So these are the steps. This is the RSA, and thank you for listening.